Good morning, everyone. We are Scube Labs, and today we'll be presenting Nesmatics, our project for the UPRM Computer Engineering Capstone course. Scube Labs team members are Sofía Saavedra Vélez, Eduardo Santiago Vargas, and Pedro Santiago Dominici. Before talking about the problem solved by our product, I'll explain some background information. Micromobility technology refers to lightweight transportation for individual use to move across short distances. On a global scale, the micromobility industry is estimated to reach $9.8 billion by 2025. Why is it so important? Well, it is expected that micromobility technology will play an important role in the development of smart cities, as it provides an essential transportation service for short commutes. One of the reasons why micromobility companies are successful is its logistics infrastructure. More specifically, the optimal design of how many vehicles to position on key areas. Not implementing this optimal design can result in profit loss, missed usage opportunities, and a non-scalable business model. Our client, Skootel, is very aware of this. Skootel is the first micromobility company in Puerto Rico and the Caribbean, and uses e-scooters as their shared vehicles. To implement the optimal design previously mentioned, Skootel operators develop drop strategies. These are plans developed weekly that list when, where, and how many vehicles to drop off. However, these drop strategies are currently inefficient. They take over 8 hours to make, are not data-driven, and the process to develop them is completely manual, which makes it more complex for operators and prone to errors. Thus, we developed Nesmatics as a solution. Nesmatics is a dynamic web application that tackles the problem's main variables: the lack of visualization tools, the manual process of creating drop strategies, and the overall time it takes to develop them. By introducing visualization tools, machine learning suggestions of where to drop off vehicles, and a drop strategy planner.
Scube Lab has successfully completed all of their milestones. As a result, the Smatic web application is now up and running on a server accessible by the client. Additionally, project documentation has been provided to the client for future management of the system.
The total cost of the project was $66,895, amounting for 99.5% of the projected cost. There were no changes made on the projected work hours, as well as the cost of the utilities and benefit incentives. Completion of the project was done within the budget, with minor adjustments made due to a slight overestimate in price for services and APIs. System specifications are in accordance to design criteria for the project. First, users needed to be able to create and manage service areas and nest configurations, as well as to visualize, write data, and extract behavioral information. These features were attained by using a combination of interactive mapping libraries like OpenStreetMap and Leaflet, an open-source interactive JavaScript library. The testing was done using Whitebox unit test and using GeoJSON.io for geographical data visualization. For the system to create predictions of expected writes, we opted for a fully convolutional neural network as our machine learning model. This was chosen for its capabilities of processing positional information more effectively compared to other architectures. To implement this model, we chose the Keras library for Python. The training was performed using 70% of the available data, and the other 30% was used for validation to measure the model's accuracy. Unit testing was performed on components of the pipeline process. The system also needed to allow users to upload data. This data is then processed and prepared to be visualized and analyzed. This was attained by deploying a RESTful API with CRUD compliant routes, and then tested using the Postman platform for API development, and using unit tests for write and nest calculations.
For the user interface, Nesmatics made use of the Angular frontend framework. Angular was chosen among other alternatives for its defined structure, as well as its extensive and well-defined documentation. Furthermore, some of our teammates had previous experience with it. As a backend framework, we used Flask. Flask is lightweight, provides more control over what libraries to use, and uses Python for its language. To store and manage the data, we use a NoSQL database, specifically MongoDB, for its document-based structure and flexibility. To implement our machine learning module, we use the Keras library because of its fast modal prototyping. It is also optimized for low-level matrix operations, which are crucial for neural network predictive and training speed.
The system consists of 4 different software packages called Docker containers that will each be in charge of a portion of the system. These containers will have all the dependencies needed by the software to ensure the application runs quickly and reliably from one computing environment to another. These containers are the reverse proxy, the front-end web server, the back-end application server, and the database container. All these containers are stored in an Amazon Web Services EC2 instance.
The team progress wasn't free of issues. Scube Labs had to spend extra time at the design phase to develop a solid foundation of the system. This delay was compensated by extra work and later a faster implementation and integration phase. You can see this pattern in the burn down graph being shown. The team also worked with some extra challenges caused by this unusual year. Communication was difficult, but the team quickly adjusted to adopt tools that will help keep Scube Labs together. Power and internet outages were common among the members, and as a consequence, overtime and task distribution was needed to finish this project. The project has multiple areas in which it has an impact. The immediate ones are what Nesmatics provides in its features, like data management, visualizations, and predictive capabilities. But also, Scube Labs has identified some indirect ones. Hopefully, it will facilitate the Skootel company to grow at a faster rate, and by helping them, also helping the general public to have more accessible alternatives to carbon-emitting transportation.
In the end, Scube Labs delivered a deployed and working prototype of Nesmatics, which met all essential requirements agreed upon with the client. Other deliverables include the complete project design documentation and the source code. All of this makes up the final product, the Nesmatics web application. Nesmatics' impact can be resumed in the improvement of the ride analysis process. This in turn helps Skootel in taking faster data-driven decisions in terms of vehicle positioning, which provides the public more readily available transportation. Some of the many achievements taken from this project were the traversal of some of the product lifecycle changes, from inception to design and implementation of a working prototype. Another achievement was the acquisition of new knowledge in multiple areas and technologies. Difficulties encountered included the fact that all our work was done remotely, which inhibited some communication aspects and caused issues when someone lost power and internet. An important lesson learned on this development endeavor was the ability to respond and adapt to changes quickly, despite stressful and demanding circumstances, and that taking the time to deeply understand a problem from all angles and directions will go a long way in developing a solution. For future development of this project, other ride and nest analysis can be added, along with more robust prediction models to provide predictions with higher accuracy. Also, being that this project takes geographical data to plan solutions and provide predictions, it could also be used in conjunction with other transportation domains, such as taxis or buses, in order to fully provide their services and meet the demand for transportation.